Hello guys, in previous video we read about various things in which error detection techniques were involved. Now these were vertical redundancy check VRC, longitudinal redundancy check LRC, checksum, cyclic redundancy check CRC. These were the four error detection techniques that we talked about. Now in this video we are going to elaborately discuss each of them. Okay, so moving to the first one, that is VRC, vertical redundancy check. Now it is also called as parity check. It just counts number of 1 in the data unit. If it is even, then it adds 0 in the beginning, and if it is odd, then adds 1 in the beginning of the data unit. What it says is, for example, suppose this is a data unit 1 1, this 0 is crossed here, it is 1 1, this 0 0 0 0 1. Now what is the number of ones here? How many ones are here? 1 2 3. 3 ones are present here, so 3 is an odd number, and it says whenever the number of ones in the data unit will be odd, it will add a 1 in the beginning. So here the parity generator will be 1, so it will add 1 in the beginning. Suppose if it was an even number, suppose this 1 was 0, then the number of ones would have been 0, 2, that is an even number. Thus the parity generator would have generated 0, then it would have been 0 1 1 0 0 0 0 1. Okay, so simply it says that vertical redundancy check says that if the number of ones are odd in the data unit, then I'll be adding 1 in the beginning of the data unit while transmitting the data. However, if there are going to be even number of ones in the data unit, then a 0 will be added in the beginning of the data unit while transmission. This is basically what it says. Now the receiver also just counts the number of ones, whether odd or even, and if matches the number added by the sender in the beginning of the data unit, then assumes it to be correct. Now when the receiver will receive this data, the receiver already knows that this one is parity generated number. That is, the data is after this bit, the entire thing is data. So what it will do is, it is going to count the number of ones itself, and then will generate its own parity. Then it will generate its own bit, and if that bit matches with the bit that is sent by the sender, then it concludes that this data is right without any error. Okay, what I said is, what we did while sending the data, the receiver is also going to do the same thing with the data. And if both of us, the counting of ones matches in both of our cases, that is in the senders and receiver case, then it assumes that this data is correct and is without an error. Alright. Now it can detect single bit error. Okay, we saw here that if it would have been 0 here, it got corrupted in the way it got 1 here, then the parity generator wouldn't have been 1, because the number of ones would have been even then, so it would have been 0. And when the receiver will check it, it finds that sender sent me 1 and what I am generating is 0. Then it concludes that this data has been corrupted. So single bit error can be detected. However, suppose 2 bits on the way got corrupted. This one got corrupted to 0. This got corrupted to 1. The data is modified, right? The data is not the same as it was sent by the sender. It is modified now. This second one, this where my arrow is, this is converted to 0. Suppose if this is corrupted to 0 and this 0 is corrupted to 1. Okay, now still the number of ones won't change. Look, 1, it got corrupted to 0, so we won't count this. but this got corrupted to 1, so we'll count this. 1, 2, 3. Number of 1s remain the same. And when the number of 1s remains same, it will come out to be the same. Okay, the receiver is not going to detect any error because I also generated 1. If I am the sender, I also generated 1 because the number of 1s were odd. He also generated 1 because the number of 1s is odd. That is why it cannot detect if 2 bits are corrupted. Okay, it can detect burst error only if the number of error is odd. Okay, so if the number of error is odd, that is 1 bit got modified, or 3 bits got modified, or 5 bits got modified, then it can detect it. However, if even number of bits got modified, then it cannot detect it, as I aforementioned and I told you earlier, explained you earlier. Now there, what I told you is written over here. Look, sender transmission error. Look, sender is sending 10 100 0001. Okay, now it is written over here. Look, sender sent, this was the original data. It got modified like this. 0, this first bit got modified into 0. Okay, so this first bit got modified into 0. This is the parity check. This first bit got modified into 0, so it became 0 1 0 0 0 0 1. It will detect it now because here it is showing that this bit is showing that the number of 1s will be odd. However, in actual, the number of 1s is even here after getting corrupted. So that's why it's going to reject. Okay, the receiver is going to reject it. However, now here in this case, 2 bits got modified. This 1 got converted into 0. As you can see, here was 1 and there was 0. However, here the 1 got converted into 0 and the 0 got converted into 1. So there were even number of error. This will get accepted because if it is going to first see that, okay, this is 1 here, that means the number of 1s are going to be odd. It checked the number of 1s, 1 2 3. It came out to be odd. So it will conclude that there is no error in this transmission and will accept it. Okay, so this was about VRC, how it works and about its performance. Now moving on to the second one, that is longitudinal redundancy check, LRC. Now in this, a block of bits is organized in rows and columns, also known as two-dimensional parity. The parity bit is calculated for each column and sent along with data. The block of parity then acts as redundant bit. Now, let me make you explain all of this with the help of an example. After that, when you're going to read this, you will understand it quite properly. So let's take an example. Now, it says find LRC, longitudinal redundancy check of data blocks 11001111, this and this. Also determine the data that is transmitted. Okay, so what it says is, in this, a block of bits is organized in rows and columns. So look at here, these were the blocks of bits. Okay, they are going to be organized in rows and columns like 1 1 0 0 1 1 1. Okay, so it is organized like this. The first block is here, the second block is beneath it, the third one is beneath that one, and like this they will be organized. Now what we are going to do is, now we are going to check it. Now we are going to find the number of ones, doing the same thing that was done in VRC. However, what we did is, we took all the blocks and placed them kind of vertically. Okay, we place the first block on the top, then second block beneath it, and so on. Placed all the blocks of data unit of data, and after that we are going to calculate the parity for each column. Like their number of ones here are odd, so 1 1 1 3 ones, number of ones are odd, we are going to add a 1 here. And similarly, doing the calculation like this for each column, we are going to generate a new block. This will be redundant block. This is going to be the longitudinal redundancy check. Okay, this block here, this block which I have written with 10 red pen. Okay, now once we created the block, we are going to send it like this. The direction of movement will be, the first block will be sent at the very first, then after the second one will be after the first one. Okay, the first block that was in the data, look, this will be sent first. After this is going to be sent. After this, after this, and at last we are going to send this block. Here you can see the LRC is in the last. Okay, so this is how we calculate LRC and transmit the data. Okay, now how the receiver is going to check it. You know that receiver is also going to perform the same thing, and if the sum comes out to be the same, then it is going to understand that there is no error. Otherwise, it assumes that the transmission was corrupted. Alright, now performance of LRC. LRC increases likelihood of detecting burst error. Look here, in this LRC, you are likely that you will be knowing burst errors more, because in VRC you were only checking a single block. However, in this you are combining a lot of blocks and then doing your error detection. Okay, however, if 2 bits from each data block is corrupted and falls under same column, if 2 bits from each data block is corrupted and falls under same column, then the LRC checker will not detect it. What does it means is, now suppose it says 2 bits of same column got corrupted. Like suppose this is a column, right? Suppose this 1 got converted into 0 and this 0 got converted into 1. Then this 1 will remain the same. Still the number of ones in this is odd. However, the data got modified, right? Thus, it won't detect it and there will not be detected any error. So this is a blunder. Okay, this is what is the drawback of LRC. Okay, now moving to the third error detection technique, that is checksum. Okay, this operation is done at the sender side at very first. Now it breaks the original message into k numbers of blocks. Whatever the original message is, it is going to break that original message into some number of blocks with n bits in each blocks. That is, the number of bits in every block will be same. There is a data and this is going to break that data into some blocks having same number of bits. Now we are going to sum all that some blocks were created. Okay, we are going to sum all the blocks, going to add the carry to the sum if any, and at the last we are going to do complement of the sum. Then we are going to find the checksum. What does this mean? Now let me make you understand that. Suppose this entire thing was data. Okay, now at first this was it, like 1 0 0 0 0 1 0 0, then it was 0 0 1 0 0 1 0 0, then it was 1 1 1 and 0 0 1 0, then it was 1 0 0 1 1 0 0 1. This was the entire data. What we did is we divided this entire data into blocks. Okay, done. Now we are adding these blocks. Okay, before addition, let me tell you When you add 0 and 0, when you do sum of 0 and 0, it comes out to be 0. Listen very carefully. When you do sum of 0 and 0, it comes out to be 0. When you do sum of 0 and 1, again 0 and 1, it comes out to be 1. And when you do sum of 1 and 1, then it comes out to be 10. That is 1 0. Okay, I said when you do addition of sum of 1 and 1, then it turns out to be 10, 1 0. And when you do a sum of 3 ones, that is 1 plus 1 plus 1, here if there are 3 ones, suppose like here 1 plus 1 plus 1, it comes out to be 11, 1 1. Now let's start the addition, this sum. So here 0 plus 0 0, 0 0 plus 0 0, 0 plus 1 1, it came out to be 1. Now there's no carry. Okay, so again doing it, 0 1 1, 1 and 1 is 10, I told you earlier. Now 10 plus 0 is 0, plus 0 is 0, 0 here, and 1 was carried to the next column. Okay, so it will be like 1 will be here. Now 1 plus 0 1, 1 plus 0 1, 1 plus 0 1, 1 plus 1 again 10, so here will be a 0 and here will be a 1. Now 1 plus 1, the zeros, and you can neglect the zeros. Now 1 plus 1, what it will be? It will be 10 again, so 0 here and 1 here. Now 1 plus 1 plus 1, but this is going to be, when there are 3 ones, then it's 11. So 1 and 1 will be, the another one will be carried on this block, on this column. Now 1 1 10, so 0 here and 1 here. Now these are 4 ones, 1 plus 1 plus 1 plus 1. This came out to be 100, 1 0 0. Okay, now up to this, it is the length of our blocks. Whatever bits are exceeding the length of our blocks, we are going to add those bits again in the block. So we picked up these 10, these 1 0 bits, and added it again and summed it again with the outcome that was not exceeding the length of our blocks. After adding that, we got 0 0 1 0 0 1 0 1. This is the final outcome that we got. So steps up to here are done. The last step says do the complement. So taking complement of the outcome, wherever you see 0, convert that to 1. Wherever you see 1, convert that to 0. After doing so, you are going to get 1 1 0 1 1 0 1 0. Whatever you are going to get after doing so, after converting the 0 in the outcome, after you are going to convert zeros into ones and ones into zeros, that thing is going to be your checksum. Alright, now here when we did the complement, we got this as a checksum. Now this block will be appended with the value, with the data. So here it got appended with the data. Alright, now how is the receiver going to check it? Now what the receiver is going to do, let me first show you that with the help of an example. So what the receiver is going to do is, it's going to collect all the blocks and place them like this. Then it is going to do the sum of all that data with the checksum sent by the sender. And when that receiver will be doing sum of the data and the checksum, if the outcome turns out to be all ones, then that data will be accepted. If the outcome is all ones, only and only if the outcomes are all ones. If any of the bit is 0, then it won't accept it. Alright, so this is what it says. It is going to collect all data block including the checksum, sum all the data blocks and checksum. If the result is all ones, then it is going to accept it, otherwise reject it. So this was checksum. Moving further, performance of checksum. The checksum detects all errors involving an odd number of bits. It detects most errors involving an even number of bits. If one or more bits of segment are damaged and the corresponding bit or bits of opposite value in a second segment are also damaged, then the sum of those columns will not change and the receiver will not detect the error. Now, what does these 3 points mean? Checksum caliber is able of detecting if their 2 bits are damaged here, that is even number of bits are damaged in a block, it will detect it. If an odd number of bits are damaged here, then also it is going to detect them, like this got converted, this got converted, this got corrupted, all 3 got corrupted, then also it is going to detect the error. If 2 of them got corrupted, then also it is going to detect the error. However, suppose one got corrupted to 0 and this another bit of the same column of opposite value got corrupted into 1. Now this became 1, this became 0. The result will still remain the same and the error will not be detected. So this is a drawback of checksum. I hope you understood what I said you. Okay, so this was all about checksum. Now moving to CRC. Okay, now first of all, let me explain it to you. Now suppose the data was, now please listen carefully, otherwise you won't be getting this clearly. So please listen carefully. Suppose the data is 100 100. This 100 is the data. Okay, what we are going to do is, at very first we are going to a divisor is going to be decided by the sender and receiver. Suppose this is the data, 100 is the data. Okay, clear? Now the sender and receiver decided a divisor. For what purpose? I am going to tell you a little bit later. Please first focus. They are going to decide a common divisor. In this case it is 1101. Okay, divisor is clear. We are okay, clear. We understood they are going to decide a common divisor. Okay, and if this is the data, we are going to now append the data. First we are going to append the data with L minus 1 bits, that is how many bits they are in divisor, 1 less than those number of bits are going to be appended in the end of the data. So there were 4 bits here, we are going to add 3 zeros, the bits will be zeros, so the 3 zeros are going to be appended at the end of the data. Clear? It became 100 100 000. Alright, now we are going to divide it. Okay, we are going to deduce the CRC. How we are going to do it? Simply do the division here, like there is 1001, put 1 here, it came out to be 1101. Now subtract it. Remember, the subtraction of two same bits is 0, same bits is 0, two different bits is 1. Okay, now moving further, look, 1 minus 1 same bits, so it will be 0, then 0 minus 0 same bits, it will be 0, then sorry, this one was of these two, so 1 minus 1 same bits, it will be 0, 0 minus 0 same bits, it is going to be 0, 0 and 1, these are different bits, so it is going to be 1. Okay, and at the end 0. Now this turned out to be 100. 1 0 0. Now we are going to take a 0 from above. Okay, again putting 1 here and 1 1 0 1. Okay, 1101 into 1 1 1 0 1. Okay, again doing the same thing, different bits means 1, same bits 0, different bits 1, same bits 0. This came out to be the outcome. Again, cause it is less than 1101 and it is less than the number of bits here, so we are going to put another 0, take another 0 from above. Okay, now doing this, we did this until all the zeros were taken from the above. This was the last 0. Okay, now what we did is, in the last we placed 1 here and did 1 1 0 1, and the outcome came out to be 0 0 1. Okay, now there is no more 0 left, and this is less than the number of bits here, so it cannot be divided further. Hence this is the CRC. Okay, remember the CRC will always be less than, always is going to be less than less than the divisor. Its bits are going to be L minus 1, that is the 1 less than the length of divisor. If they are 4 bits, then they are going to be 3 bits in the CRC. Okay, we got the CRC. Now CRC came out to be 001. Now the data transmitted will be 100, 100 and 001. That CRC is going to be appended in the last. Alright, how the other person is going to check, how the receiver is going to check whether the CRC sent by this, the CRC sent to me is right or wrong. The data transmitted do have an error or not. Okay, so what it is going to do is, it is going to take this entire bit, this entire block. This entire block is going to be divided again with the common divisor that was decided earlier. Alright, so this entire block, this 100, 100 and 001 is going to be divided by 1101. So just place this block in the place of this block. Okay, now if it came out to be, the remainder came out to be all zeros, then the data is correct, otherwise it's wrong. Okay, so yes guys, this was all for today. Thank you for watching.